So, welcome all to the third session for the course Geotechnical Engineering 1 problem solving session for the course Geotechnical Engineering 1. Uh, I am Yogendra Narayanan. I am a PMRF research scholar who will be handling these sessions uh, usually on Saturdays from 5 p.m. to 7 p.m. But due to some unforeseen circumstances, I had to prepone this session this week on today. So uh, I have uh, intimated in prior to the NPTEL handling team, and most probably I think you have not seen the NPTEL website. That's why um, you have not joined it. So today we will be discussing some concepts regarding the behavior of soil, its deformation mechanisms, some properties, basic properties, mineralogies uh, for different type of soils, their arrangements, etc. So before going into the actual quantification and numerical estimations of these parameters, we need to have a fundamental understanding of how the soil structure is arranged and what are its composition and how to determine it, what are all the various techniques that are used to determine this, what are all the basis for those techniques. So these things have been briefly discussed in the past week of geotechnical engineering one. So with this, so this week also will be mostly largely theoretical, means some verbal questions. Most probably from next week it will be more of numerical types. So again, I would like to emphasize that these sessions are intended to make the learners proficient in the subject by solving the previous assignment problems or questions to make the basic clear so that they can confidently face the NPTEL final examinations as well as their university examinations, also several other competitive examinations. So this sessions, I hope it will be useful for you. So I would like to again uh, emphasize that your active participation is highly encouraged. So you can um, try to join in time. Uh, so try not to miss any sessions in order to continue with the continuity, and most importantly, please uh, watch the lectures that has been uploaded in a particular week before coming to the session, so that you have a background idea of the concepts that have been taught, and you don't find it anything alien in the problems which we solve. So this session is not essentially a teaching session, uh, but it is a practicing session. So uh, there is uh, there is no logic in expecting again the same contents to be taught in a separate session that here. So essentially, it is a problem solving session. So people are advised, the learners are advised to watch the uh, complete content of the course that has been uploaded in the NPTEL website in a particular week and attend the sessions here. So with this, we will be entering into the session. Uh, Let me just share the screen. Is it visible now? Just a minute, there is an issue. There is a connectivity issue. Just a minute. It's visible. So, welcome to the problem solving session, and it is handled by Professor D.N. Singh, and we are from Department of Civil Engineering, IIT Bombay. So, coming to the first question of today's content. So, the specific surface area is defined as specific surface area SSA is defined as option A total surface area per mass, total surface area per volume, and total surface area per thickness, and total surface area per length. specific surface area is defined essentially as total surface area per volume, sorry, mass. Total surface area SSA is equal to total surface area TSA by mass, right? Now, how to calculate it? Specific surface area is defined as total surface area by mass. Now, let me give you a simple condition of rectangular arrangement like this. Arrangement, cubical arrangement. This is known as cubical arrangement. This is one of the simplest grain arrangement that is present. So now the center to center distance is D, right? This is D. Now total surface area is, it has six faces. This one and this one, top and bottom. 1, 2, 3, 4, 5, 6 down. So total surface area and the area of one face will be area of one face is D square. So DSA is 6 faces 6B square. Right. Now coming to the mass. So mass we cannot calculate, but it can be calculated indirectly by the relation, basic relation. Mass is equal to density into volume. So here volume of this cube will be D cube and density is rho, which can be written as specific gravity into gamma W. So substitute in the SSA equation. SSA is 6D square by GS gamma W D cube. This will get cancelled. This will get cancelled. So from this, what we are able to observe is SSA is indirectly proportional to D. All right. So D is an uh, indirect measure of particle size. Indirect, or it is a direct measure of, it is the particle size. Particle size. So lower the particle size, specific area, so specific surface area will be higher. So that leads us to the next question. Right. So increase in the specific surface area leads to option A, reduction in particle size and activity, increase in particle size and activity, increase in particle size and reduction in activity, reduction in particle size and increase in activity. So what we are able to observe is SSA. Once SSA is increased, that means the particle size is decreasing. So these answers are straight away reduced. So one specific surface area is more. The region, that is the area available for interaction, is more. Any interaction with other what to say, components is increased. So ultimately, the activity of the brain uh, becomes higher once specific surface area starts to increase. All right. So that will, the activity is actually a quantifiable term. So which we'll be studying later on when we study particle size analysis. So that time we'll be coming back to this exact quantification of the activity. Especially activity is a term related to clay size particles. So that is what it requires some understanding on index properties, which you will be introduced further in the course. So right now you can simply understand that activity is only is a depiction or is a representation of how uh, open the grain is to interaction with other components. So that is known as activity. So once a specific surface area is increased, the area available for this interaction increase. So that will in turn result in increase in activity. So this option turns to be wrong and this option turns to be right. So any doubts? So let us move to the next question. Which of the following instruments can be used for the elemental analysis of soils? Which of the following instruments can be used for elemental analysis of soil? Option A, X-ray diffractometer. Option B, scanning electron microscope. Option C, X-ray fluorescence spectrometer. Option D, all of the above. So to understand this, we should analyze one, or we should see the application of each one of the. Just a minute. Right. So coming back to this, we should analyze. So X-ray diffractometer. X-ray diffractometer is essentially used in identifying minerals as a whole. Identifying minerals. That is, it gives a quantification of minerals. That is quartz or kaolinite or montmorillonite or calcite etc. So it gives identifying of minerals. Scanning electron microscope, coming to this, so it is essentially used to understand morphology of the soils as well as some idea about the elements present. So, fine. So X-ray fluorescence spectrometer gives you the breakdown of what are all the oxides, especially oxides. So quartz is essentially SiO2 and alumina is there, Al2O3. If it contains iron content, Fe2O3. Magnesium hydroxide and it tries to break down the minerals and gives you in the terms of oxides. So that is used. So coming to this, the complete comprehensive elemental analysis and their arrangement can be studied as a whole by using all the three. So the right option will be all the above. Okay. So question number 4 is XRD works on the principle of option A, Beer-Lambert's law, option B, de Broglie principle, option C, Bragg's law, option D, none of the above. So we need to understand to coming to this question, XRD works on the principle of there are three different laws. So which we have been introduced, or we have been all we all have been introduced in our higher secondary schools. So Beer-Lambert's law is essentially used relates the light absorption, which is used in spectrophotometer analysis. Spectrophotometry analysis. Right. So de Broglie's principle, we know that it is dual nature of light, wave particle equation. And coming to Bragg's law is what? So when you have two crystals which are separated by a distance d and you pass X-rays of some wavelength, it gets reflected. So this pattern, it gets incident at the angle theta and the order of the X-rays, let it be n. So the relationship exists like n lambda is equal to 2d sine theta. All right. So this gives you, so we know the order of the X-rays we use, we know the wavelength of the X-rays we use, we know the angle of incidence. What we get is, we get the D, right? So for several angle of the plot is uh, plotted between the that is the theta and several wide range of theta is used and we get the interplanar distance. So based on the interplanar distance, we try to quantify there is a complete database where each distance for each peak you get a corresponding mineral. So usually it is done by a software called Expert High Score. You can search it in net where you can get the full complete database for XRD analysis. So based on this interplanar distances, minerals are being, the type of mineral is being identified and estimated. All right. Oops. So the XRD is what XRD works on the principle of Bragg's law. So the right option is option C. Right. So coming to the next part, next question. Which of the following deformation mechanism is negligible in case of soils with rigid boundaries? It's negligible in case of soils with rigid boundaries. So rigid boundaries in the sense, let us draw the schematic of a rigid boundary condition. These are not deformable. Volume remains constant, and this is what we are using to apply a load. These are the greens. So now the question is, which of the following deformation is negligible in case of soils with rigid boundaries? So once it starts to press, so there is nowhere the particle can, initially there might be some rearrangement, uh, but at the, it is not predominantly rolling. So once the load is being applied continuously, so it at over a particular pressure due to the uh, sharp edges, if there is a presence of sharp edges due to the edges of the grains, the stress localization will occur, and it will cause sudden rise in stresses at the contact points, so that may result in some crushing of the grains. So crushing is a significant phenomena that occurs here. And compared to coming to clay type of soil, there is a clay or essentially a flaky structure where the edges are positive and the surfaces are negative. All right. So, and now when we apply the load, so it tends to bend due to its flaky nature and because of its slenderness ratio. All right. So tends to bend. So in a significantly in a clay soil, in a specimen of clay soil, when the same load is being applied, so the predominant deformation mechanism is bending. So this is also a predominant mechanism. Coming to rolling, rolling initially causes, in case of rigid boundaries, in case it causes some initial deformation, but it gets predominant in uh, flexible boundaries where it can roll over one to accommodate the uh, increase in the uh, uh, boundaries. So it is the yeah. So the increase in the boundaries. So in case of rigid boundaries, the negligible phenomena or negligible deformation mechanism is rolling. So this option is the right one. All right. Now coming to the next question. Which of the following mechanisms are predominant in the granular soil? So the following mechanisms are predominant in granular soils. Granular soils are essentially also in geotechnical terms are termed as frictional soils, fine, coarse grain soils, where the body forces become significant. The body forces are significant, and that is body to body contact, which is friction. Predominant in granular soils are friction. So there is another term called apparent cohesion, which is not an inherent property of the granular soil, but it develops due to its in, its interaction with the pore water. So which we will be studying later in uh, the course. All right. So coming back to this question, the mechanism which is predominant in the granular soil is friction. All right. I hope there is no doubts, and it is apparently very. Uh, it's a it's a clear answer. Sorry, 1 minute. There is an issue with the sharing because of network connectivity issues. Just a minute. I will try once again. So coming back to this next question. So the clay particles, question number 7 for today, clay particles are surrounded by dash layer. So clay particles are surrounded by dash layer that is adsorbed water, free water, double layer, and option D, none of the above. So if for this to answer this question, we need to understand how uh, this clay, uh, s- how to do it? How clay water interactions occurs. So first of all, let us draw a clay particle. It's usually flaky. So for convenience, I'm drawing like this. So the edges are positive and the faces are negative. Alright. So here cations are absorbed in a very large manner along with water. Right. So so this layer, and there is another layer where the cations are loosely bound. Here there is free water. Right. So now done. So now this layer is called as stern layer. S-T-E-E-R-N. Stern layer. And this is termed as GOIS. G-O-U-Y. GOIS diffuse layer. Right. So now this is a layer and this is a layer between the free water and the clay surface. So this is known as these two layers combinedly are known as the diffused bubble layer. Right. So this is known as diffuse double layer. So as a whole, if we consider the clay particles are surrounded by which layer? First layer is turn layer or adsorbed water. Adsorbed layer. Adsorbed water layer. So ideally, the clay particles are first surrounded by adsorbed water layer, which is the right option. But as a whole, what is the complete layer as a whole? That is how water is interacting with the clay particle is by in two stages, which is I I would not say stages by two layers in two layers, which is the stern layer and second is diffuse layer, which are collectively termed as diffuse double layer. All right. So ideally speaking, technically the right answer would be adsorbed water. All right. So I hope this is clear from this from the part. And question 8, coming to question 8, vitrification involves applying which energy to the soils? So vitrification, you might have heard vitrification. So vitrification is a process in making tiles from clay. So where you give enormous amount of heat to make the clay stiff and to uh, how to so it makes it dries up the water and it holds the water which are bound to it and it 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 uh, it protects the integrity of the clay structure as such by imparting thermal energy and making it stiffer. So for using it as either ceramics, tiles, pots, etc. So that is known as vitrification. So and essentially vitrification involves applying thermal energy to the soils. So you can read more about vitrification. So that is not the scope of the subject, but it is uh, a energy energy field in which soil interacts with uh, the environment. All right. So this is so that's why this question has been included. Vitrification involves applying which energy to the soils, which is thermal energy. All right. Standard. Standard. So this right. Now coming back to this question of this question 9 of this week. Which of the following statements is not correct? Which of the there are four options given, of which we have to choose which is not the correct statement, which is not factual. So option A, water can take only compressive stresses and no shear stresses. Option B, pore water dissipate faster in the fine-grained soils. Option C, organic matter imparts compressibility to the soil. Option D, the moisture absorption capacity of clays follows the trend smectite greater than elite greater than kaolinite. So let us analyze these options one by one. Water can take only compressive stresses and no shear stresses. Uh, to answer this question, so this statement is true. This statement is true. Is because water does not take shear stresses. That's why we are unable to walk on water. So unless it has shear stresses, so soil possesses shear strength. That's why we are able to walk on it. Once the soil loses its shear strength, uh, that is termed as in one way it is termed as liquefaction of soil, where soil loses its shear strength, where it takes it uh, becomes devoid of taking any load upon it, so that for example we cannot stand on those soils which are liquefied, which possess no shear strength. So and water takes compressive strength stresses. It is almost incompressible fluid, so it resists compression, but it cannot resist shear strength. All right, shear stress. So this statement is true. So pore water dissipates faster in fine-grained soils. So pore water dissipates faster in fine-grained soils. Fine-grained soils are essentially made up of particles which are lesser in size by several magnitudes, almost three order magnitudes compared to coarse grained soil. So which in turn uh, infers that the s- the path available for water to dissipate on the application of load is lengthy, and it has to trace a lengthier path through the pores, so which makes it faster, uh, which makes it faster for coarse grained soil, and it is slower for fine grained soil. So this statement is false. Coming to the third option, which is organic matter imparts compressibility to the soil. So that is obviously true because of two reasons. One is organic matter has the tendency to hold water, and second reason is when once the organic matter starts to decompose, it tends to the once organic matter in the soil starts to decompose, it results in almost a collapse of the soil. So that is reflected back in the compressibility aspect of the soil. So organic matter imparts compressibility to the soil is a true statement. And the moisture absorption capacity of clays follows the trend. Smectite, illite, and kaolinite. So smectite is nothing but is cousin is falls under the same umbrella as montmorillonite. Illite is we will study what is illite and kaolinite. So here the moisture absorption capacity depends on the specific surface area. Specific surface area of smectite is around 800 meter square per gram. Illite it is 100 to 120 meter square per gram, and kaolinite it is around 10 to 20 meter square per gram. So moisture is more absorbed in smectite followed by illite and kaolinite. So hence this statement is true. So the statement, the false statement which is not correct is option B. So this is the answer. So which of the following is not a mechanism of deformation of soils? A. Particle crushing. B. Particle bending. Option C. Particle rolling. And option D. Particle slipping. Particle crushing we have discussed already, where the particle tends to crush when the edges or the uh, sharp edges of the grains meet each other, resulting in stress localization. There is a sudden increase in the contact stresses, which results in particle crushing. Particle bending essentially occurs in place which has a flaky structure, uh, and particle rolling is by which the particle deforms in the presence of flexible boundary conditions on the application of external load. And option D is particle slipping. Particle slipping is not essentially a term. The particle rolling, since if the deformation, the slipping occurs in form of rolling. So the option the answer for this question, which of the following is not, which is not the mechanism of deformation mechanism of the soil, is particle slipping. All right. Any doubts? So we'll take a short break. So we'll meet in 5 minutes. Let's see the further questions. Just a minute. There is an issue, internet issue. Just try to um, project it again. Data estimate. Just try it once again. Yeah. So this now coming to the question 11, which of the following statements is correct? Bacteria preferably attached to the face of the clay particles. Bacteria preferably attached to the clay of the face of the clay particles. Isomorphous substitution is the capacity to attract cations from water. In clays, cation replacement ability is greater for smaller valence ions. So option D, cation concentration increases with an increase in distance from the clay particle in water. Right. So bacteria essentially bacteria are essentially negatively charged particles. Alright, sorry, particles, not particles, organisms. So this is an ideal structure of clay. This is the negative charge at the edges and positive charge, sorry, negative charge at the faces and the positive charge at the edges. So bacteria are negatively charged organisms. The net charge is tend to be negative. So they don't get attracted at the face, they get attracted to the edge. So this statement is false. So coming to the next option, isomorphous substitution is the capacity to attract cations from water. So first we should understand what is isomorphic substitution. Isomorphous substitution we'll be studying more is the ability for a cation to replace one another cation of similar size and charge. All right. So it's just a substitution of cations from one cation to other. So it can be either sodium to magnesium, silica, aluminum. So this changes, it alters the net charge of the uh, clay particle, and it also changes the nature of the mineral. So one is uh, Na, that is sodium replacing uh, silicates. So when sodium is present, it is known as Na-maltmolonate, and if calcium is present, it is known as calcium maltmolonate. So silica and aluminum are interchangeable in some minerals. So I'm not going into these micro details, but this replacement of the cations from either it can be from water or anything, similarly sized cation, similar sized cations are is termed as isomorphous substitution. So this statement is right. So coming to the third option, which is in clays, cation replacement ability is greater for smaller valence ion. So as I mentioned, this cation replacement ability is uh, how to put it. So the lower the valency, the lower the cation replacement ability. So that is the relationship. So this statement is also false. And coming to the next next option, cation concentration increases with an increase in distance from clay particle in water. As I already referred to this previous diagram of clay structure, uh, where there is a negative charge and the positive charges at the stern layer, followed by the positive charges at the diffuse layer, and followed by free water. So the graph is such that with the distance from, sorry, if this is the face of the cation and this is the distance from the face of the cation, sorry, face of the clay particle, the cation concentration distance tends to decrease. There's approximately an exponential decrease. So hence this option is also false. So the right option is among these statement is isomorphous substitution is the capacity to attract cations from water. All right. So coming to the next question number 12, the activity of the soil particle depends on the activity of the soil particle depends on option A volume, option B density, option C total mass, and option D specific surface area. So as we already discussed, the activity of the soil particle depends on specific surface area. So specific surface area is the denotion of the area which is available for the interaction to take place. So that indirectly gives the it is a uh, uh, measure of activity. All right. So this is a fairly straightforward question. So the right option is option D, specific surface area. Now coming to the next question number 13. So the type of forces occurring within the soil grain. The type of forces occurring within the soil grains. Option A, body forces. Option B, surface forces. Option C, neither of the options mentioned. Now coming to this, so soil grains are broadly divided to coarse and fine, right? So coarse grain soil and fine grain soil. The coarse grain soil are the forces are dominated by its self weight, which is especially self weight, which indirectly gives rise to friction, right? Which is a body to body force. All right. And one more thing I want to forget to mention is this interaction between the ion and the negatively charged surface in clay and positively charged cations. This in the diffuse double layer is purely it follows Coulomb's law, right? So it follows Coulomb's law. Now coming back to this, so fine grained soil, due to their charged nature, their and the charges are essentially, as I mentioned earlier, it is at the face or its surface. It's the surface. So that's why these surface forces are essentially electrostatic forces, Coulombic forces, electrostatic Coulombic forces. Self-weight friction. These are body forces. These are surface forces. Right. So coming to the soil, since the question essentially specifies or broadly specifies only soil grains, so both the type of forces occurs, which is body forces as well as surface forces. All right. Now coming to the next question. Just a minute. I'm just getting a call. So coming back to the discussion. So both body forces and surface forces act on the soil grains. So if the question was more specified to coarse grained, then the option would be body forces. And if the question was intended for fine grained soils, then the right option would be surface forces. All right. Now coming to the next question. Arrange the ions, aluminum, lithium, and ammonia in the increasing order of cation exchange capacity. Now, the ions of aluminum, we know the valency, it is +3, lithium is +1, and ammonia is +1. Now, coming to this part, we know that higher the valency, higher the cation exchange capacity. So, these options are can be eliminated. So now the option remains whether ammonia is lesser or lithium is lesser. Now coming back to this, we need to understand in this case when two valencies are same, then the atomic radius, that is the ionic radius comes into picture. Ionic radius. So in this case, ionic radius of lithium is less than ammonia. So hence, ionic radius of lithium is less than ionic radius of ammonia, right? So that's why this lesser the ionic radius, lesser the cation exchange capacity. So then comes this among these two options, this is not right. So this is the right option. So lithium followed by ammonia followed by aluminium. Many doubts? Many doubts. I think it's clear. To the next question. The net charge in a clay particle is net charge in a clay particle is we know that clay particle is positive, negative, negative. So since the phase are more exposed and it tends to attract cations more than anions, the net charge in clay particle is considered to be negative. All right. So which of the following grain structures prevails in clays? Single grain structure is just the arrangement, neither tetrahedral manner or octahedral manner, which is um, prevalent in coarse grained soils or sands, right? Especially sands, single grained structure. Flocculated and dispersed. Flocculated and dispersed are in case of clays. Ideally, it looks like this, but for simpler understanding, we just this is the phase, positive, negative, and the negative charges of the clays tracks like this, and the positive charges of the clays attracts like this. This is edge to face or edge to edge connection. Edge to face or edge to edge. Edge to face, edge to face, or edge to edge connection. Right. So that is the this refers to flocculated structures. Right. And dispersed is where due to the some of the external agencies, it tends to arrange like this. Positive, negative, negative, negative. positive, negative, 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 positive. This is face-to-face arrangement. Face to face. This is dispersed. Both are exclusive to only place. These are place, not right. And honeycomb structure is like is a thread of small good connections, which is essentially formed in cells. Right. So coming back to the question, which of the following grain structure prevails in place is flocculated and dispersed. Flocculated and dispersed. Any doubts? Stem. Oh,
What I ate in a day as a working mom of two kids. Katlama. Morning எழுந்த உடனே as usual ஒரு
coming to this question 17, what type of grain arrangement prevails in flocculated clays? What type of grain arrangement prevails in flocculated clays? Option A, edge to edge. Option B, edge to face. Option C, face to face. Option D, all the above. As I discussed earlier, so the type of grain arrangement which prevails in flocculated clays is these two are for flocculated. This is for dispersed. Right. So the options are option A and option B. Coming to question 18, match the list 1 with the list 2. So these parts we have discussed, I have briefly discussed earlier. Sands, this list 1 gives the type of soils and list 2 gives the type of structure which predominantly exist, in which these soils predominantly exist. So sands exist in single grain structure, silts exist in honeycomb structure, and clays exist in flocculated structure. All right. So oh, sorry. Is it visible now? Coming back to the, since this there was a connectivity issue, coming back to this question 17, what type of grain arrangement prevail in flocculated clays, which is edge to edge. Edge to edge, as I discussed earlier, edge to edge and edge to face are for flocculated, and option C, face to face, is for dispersed. So these diagrams we have seen in the earlier slide. So which is due to the charged nature, where there is an edge to edge, edge to face, and edge to edge. And due to some external agents, or especially during loading, so it is formed as dispersed. This is face to face arrangement. All right. So coming to the question, coming to question 18, match the list 1 with the list 2. List 1 is sands. List 1 depicts the, sorry, list 1 uh, uh, what is that? Uh, shows the type of soils, and list 2 shows the type of structure which predominantly exist, in which these soils predominantly exist. So coming, list 1, sands predominantly exist in single grain structure, followed by silts in honeycomb structure, and clays in flocculated structure, which is among the given options. All right. Now coming to the next question, clay minerals. So this question is also a follow-up question. So clay minerals is essentially a flocculated structure. Organic matter is peat, intergranular cement. Intergranular cement is usually like a honeycomb structure. The intergranular cement are like this, two grains are there and some cements are being formed. So this might be either of silicates, silica, or calcite, which I've already talked about, calcite precipitation, which is essentially artificially artificially generating intergranular cements, MICP and EICP. Alright. And primary rock minerals are essentially quartz feldspars. For example, those predominantly exist in single grain structure. Quartz is essentially SiO2, which exists like this. Its valence is 4, which is like this. But single grain structure. Uh, Primary rock minerals, single grain structure. Alright. Any doubts? So coming back to this question, match the following clay minerals with the type of bonds present in them. Elite, smectite, montmolonite, kaolinite. Now we have to understand before this one, what are all the structure of these clays. Structure of this clays. Sorry for this. So today there has been a lot of internet disruptions since the venue has changed. Okay, coming back to this, match the following clay minerals with the type of bonds present in them. So first is elite, smectite, montmolonite, and kaolinite. So there are two types of essential arrangements yeah, when it comes to clay minerals. One is tetrahedral arrangement. Tetrahedral sheets. Which is sheets. They are also known as sheets. So tetrahedral sheets are usually silica sheets. Silica, SiO2 sheets. The arrangement is like this, and they are denoted by a trapezium. This is silica sheet. All right. Now, second type of sheet arrangement is octahedral. Octahedral sheets. Octahedral sheets, which are essentially alumina sheets. Alumina sheets, which are denoted by rectangle Al2O3. All right. Now, this arrangement, when there is a alumina sheet connected to a silica sheet. Alumina sheet, silica sheet, again sheet, silica sheet. So this a single unit of this is type 1:1 arrangement. 1:1 arrangement of sheets. So in case of kaolinite, kaolinite is essentially bounded by these comprises of these sheets which are bounded by hydrogen bonds due to the presence of these are hydrogen bonds, H bond. So kaolinite is a 1:1 sheet, H bonds. Right now, the other type of sheet is 1:2 sheet, which is essentially alumina sheet, which is sandwiched between two silica sheet. Alumina sheet sandwiched between two silica sheets. Silica and so on. Now, when there are two cases, when there is a these two sheets are bonded by van der Waals forces, which is a weak attractive force. Van der Waals forces are weak attractive force. This essentially occurs in Montmorillonite and smectite. Smectite is nothing but the isomorphic substituted form of Montmorillonite. And when this bond is, it contains of potassium bonds, K bonds, is essentially elite. So that's why when water enters into this hydrogen bond holds this structure together. That's why kaolinite swells less. It swells less. And potassium bond relatively holds this together and hence this is moderately swelling. This since van der Waals forces are weak attractive forces, when water enters into this, it can hold water as well as it tends to expand. So this is highly swelling. All right. So coming back to this question, so elite is potassium bond, smectite and montmorillonite are van der Waals forces, and kaolinite is hydrogen bond. All right. I hope this is clear. So what I'm trying to do is I'm just trying to relate the concepts that has been taught in the class to the application part. Right, just it acts as both a practice session as a revision session. So coming to this last question of today's, so it's a short numerical in how to understand how cation exchange capacity is calculated. So the question goes like this: 100 gram of dry soil sample absorbs 300 milligram of calcium. So the cation exchange capacity of the clay is, so the unit of cation exchange capacity is always 100 grams of milli equivalent per 100 grams, milli equivalent plus per 100 grams. Now, how CEC is defined? CEC is defined as absorbed heat by equivalent weight. It's defined as the absorbed weight by equivalent weight, which is the cation exchange capacity, which is the capacity to absorb the cations. Now, calcium. Calcium as an ion has, this is how calcium ion is depicted. Now, how to calculate equivalent weight? Equivalent weight is defined as atomic weight over valency. Right? Now, atomic weight over valency. So, the atomic number of calcium is 20 and the atomic weight is 40 and valency is plus 2. That is 2. Either it can be deprived of electrons or it can be in excess of electrons. So atomic weight is 40 by 2, which is equivalent weight is 20 grams. Now absorbed weight per 100 grams is 300 and the equivalent weight is 20. Now it is 15 milligrams, which is converted to milli equivalent per 100 grams. All right. Any doubts? So if it is sodium, if it is sodium ion, the valency is 1. Sodium's atomic weight is almost 23. Atomic weight and equivalent weight will also be 23. Now CEC of sodium is 300 by 23. 300 divided by 23, which is 13.04 milli equivalent. Now we can see that once the valency starts to decrease, the cation exchange capacity is decreasing. So this 20 grams is greater than 13.04 grams, right? So that is how valency plays an important role. All right. So with this, today's session comes to an end. So it is a fairly shorter week, so hence we had to wind up a little earlier. So Thank you for attending. These videos have been recorded and will be uploaded in YouTube, and the links will be shared with you in the NPTEL pages, and the slides will also be shared for your references. So you can make use of this. People who are unable to attend, or who were unable to attend selected sessions, can always be uh, updated by referring to these video links, and you can practice at your own availability or own convenience. So expect active participation from your side. So, and one more thing is the session on 21st February. The session on 21st February, Saturday, has been postponed to 23rd February at the same time, 5 p.m. to 7 p.m. It's just a small change due to some unprecedented circumstances. So I would like the learners to note it down. The same will be uploaded in the updated. That is, the information will be updated in the uh, website, NPTEL website also. Please try to check these NPTEL websites regularly. And before coming to this session, try to come, uh, try to attend after going through these lectures of the particular week, so that you might not find any difficulties in uh, at least having an idea of what is being discussed here. So apart from that, these sessions, apart from the exception, this session will be run every Saturday from 5 p.m. to 7 p.m. regularly. So try to attend these sessions, and once you are attending, please try to maintain the timings of these sessions. So otherwise you will miss the context, or you miss some questions, or you miss some concepts, questions explaining some concepts. So these things are crucial, which may act as crucial things. So with this, I try to wind up this session. So thank you for attending. So this from next lecture onwards, sorry, next session onwards, it will be most of the things will be most numerical. I hope we will be solving some questions. There will be scope of more involvement and discussions. Uh, so I look forward for this interactive session, for the next interactive session. Right. So let me just stop sharing my screen. So have a nice day. And I also wanted to add that I offer my apologies uh, for today's session due to several interruptions due to poor internet uh, internet connectivity, as well as some background noises which have been constantly undergoing. So I sincerely apologize for this, and I I assure you that I will take good care from next session onwards to minimize these disturbances. Right. So thank you for attending. Thank you. Let us meet next week. Thank you. I'm just closing this session.